That's why I couldn't be there. The topic which I am expected to cover is materials and process selection for circular manufacturing. And I have added many more slides in this for the background of attendees, but sometimes I may be skipping them uh, to cover in the time whatever I wanted to convey. Now, you have already attended Professor Anurup's first lecture, and then you will be attending next tomorrow morning Professor Takata's lecture about design for circularity and all that, life cycle. So you already know that what is the linear versus circular manufacturing model. So we all know typically it used to be materials. Dr. Anurup, is my cursor visible?
No, can you move?
Is my cursor visible?
Yes, it's visible.
Yeah, thank you. Material supply, and then you do the design and manufacturing, and you do the distribution and use, and then end of first life. Okay, and after that, most of the times it used to go for recycling, and sometimes it used to get landfilled. But as we all know, the resources are depleting, and if someone wanted to continue that process, we may need many more virgin materials, and then that much is not available. So that is the reason why the circularity is very, very important. You have to reuse them and all that. You have understood that at every stage we have to reduce, and then we have to reduce whatever the resource it is. Okay, and then reduce, reuse, refurbish, regenerate, recycle, all that you have heard. I don't want to get into that part here, but this slide conveys that linear versus this thing. Now, in addition, we all know that evolution of manufacturing part. Okay, we started with manual manufacturing, then Henry Ford era of mechanization, then the automation came, hard automation, soft automation. Basically, prior to Henry Ford, mechanization, when the steam engine was there, automation came, hard automation during the Henry Ford era, soft automation later, integrated manufacturing, which combines, which integrates today with the help of internet, cyber physical systems, and whatnot. You all know that all are connected devices, connected environments, and all that. Now, how the manufacturing is changing, you all know with time, particularly at present time, if you are observing in the trends, it is much more uh, complex. The mass production to mass customization, there was basically saying as long as its color is black, I can supply anything. Okay, that was the once upon a time statement. Okay, now everyone wants their variety and then customization, and people prefers that. Now you can clearly see the definition: ability to produce singular customized component product with the same efficiency as that of mass produced component without much additional cost maintaining the same quality. Now you all know, you can see from this diagram, mass production, okay, the cost is very low, but the customization is also low. But people want cost to be low, at the same time customization to be very high. This is a, in addition, you can clearly see the dateline, how it is changing. But around 2000, globalization, regionalization, complexity, and then there was a offshoring earlier. Now there is a reshoring concept. Basically, everyone wants to have the manufacturing in their own area, domain in the country. Okay, that you all been hearing that. Now, manufacturing is becoming more and more complex. Okay, now some of these slides I'll skip. Whenever you are thinking of manufacturing, there are basically a block box, customer needs, raw material will give, societal pressures, government regulation, company plans, policies, So many other inputs will be important. You need to maintain those constraints, and you have to put in money, people, machines, automation. Then the components and products will come in that block box. Another way to simply look at it as a production floor: raw materials, energy, information necessary for the component geometry, product geometry, then the component and product will be coming out. But another important thing, which is a very, very important when it comes to education part of it, is when you are looking at it, all these things play a very important role. I will not be getting into any of them in this slide, but just to touch: material science, statics, dynamics, thermodynamics, fluid dynamics, heat transfer, whatnot. Okay, all that will play an important role because a machine is rotating, component chip is getting generated, or deployation is taking place. In addition to raw material and machines, then you will be assembling those components, and then you will be producing the product. Okay. Now, if you see the engineering product realization, all of you are aware that it starts from product specification, depends on the market needs, design and synthesis. Today's main thing is design for X, or design for circularity, or whatever it is. Design, representation, and analysis will come. You evaluate. Then there are basically iterative steps here, and then manufacturing planning, manufacturing execution, and inspection. Okay. Now, in the good olden days, they sometimes they never used to bother about the manufacturing process here. They used to design, and then they used to think about the manufacturing process later. But later on, considering for the design for manufacture, design for assembly, design for other things are also very, very important during the design, because design is the one which commits a lot of things, but you may not be spending by then. Cost incurred may be less, cost committed will be very, very high. One has to plan ahead all those things, all the downline cycle applications. Now, as today's topic is mainly the materials selection and process selection. Now, if at all you take aircraft wings, okay. Now, the material must be whatever you select the materials, and then processes, and then the shapes which you select. Then, if at all everything is perfect, if it is stiff, it should be strong, it should be tough, it should be light, everything is okay. Now, if it is not stiff enough, you need to go for bigger E. You all know the Young's modulus. Okay. Not enough, not strong enough, then you have to go for higher yield strength materials. Okay. Now, not tough enough, toughness coefficient. Okay. And then it's too heavy, then you need to reduce the density. Now, when you wanted to select the materials or materials combination, and then processes to process those materials and select the appropriate ones, it's not that easy to satisfy all of these. There must be a systematic process, particularly in the classified area like this, is where the reliability necessary is very, very high. Generally, people go with tested materials, tested things. The regulations are very, very strict. But in many of the applications, you can select, you can explore many newer materials which are getting added day by day, many of them. Okay. To know that, one has to have some systematic approach. Now, if you look at processing routes, how you process, let's say you can clearly see this is the plug body. If at all a million components are necessary, and if you go for machining, it will cost 3.9 units. And then if you go by cold forming approach, it will cost only 1 unit. Okay. At the same time, if you see the productivity and the mechanical strength when you machine the cast part, now you cannot induce the flow directions, and then you cannot induce the strain hardening, you cannot exploit the strain hardening properties. But when you use cold forming, you can exploit that. So, but the thing is, which process to be used also will be dependent on one of the factors is the number of per annum. Now you take the plug, if you go for machining, bronze one, cast one, if you machine, then it will be 2.2 units. If you take the powder metal sintering, it will cost only 1 unit. Okay. Now, so you can clearly see the context in which one has to think about it, but that is still convenient. But if you take the circularity into effect, further things gets complicated. Now, if you see the product life cycle, Professor Takata might be discussing very extensively tomorrow. Yeah. Now, you start with the need, product design, manufacturing assembly, packing and delivery, sales and service, recycling. Okay. But here, there's no circularity aspect involved in it yet. Okay. You will be learning more and more as you move ahead. Now, if among these, if you look at it, which casts the biggest shadow is very, very important. The design, you may be incurring only 5 to 10% of the cost, but your commitments will be very, very high. The decisions which you take here. Okay. Now, let's say with our background, we can easily appreciate if you choose very tight tolerances to achieve them, the manufacturing processes necessary will be very, very different, and then the cost you're committing is different. Okay. Just for example, like that, you can clearly see design stage one must be very, very careful. Okay. If you see the information flow and back, okay, from product design within the shop floor, within the inspection units, okay. Now, whatever you design, sometimes you'll be going for manufacturing process, but before going to manufacturing process, then you may have to design the tools and then make those tools, then only you can go for a manufacturing. You may be going for NC machining and then NC program machine, but that component must be checked whether it is produced to the right dimensions, right properties necessary, surface properties necessary. For that, you have to once again come back to the product design data and then go for the inspection. Okay, so whatever the data which you are generating also in the integrated platforms today is very, very important. This also must be compatible with all the downline applications. Okay. Now you can clearly see that is what the cost committed versus cost incurred. Now you can see conceptual design, detailed design, manufacturing, distribution, servicing. The cost committed is 85 to 90%, almost 85% by the time you complete the detailed design. But the cost incurred, you can clearly see maximum 20%, maximum. Okay. Now, if you can basically incorporate whatever you need at the initial stages, then during the design stage, and then foresee what is going to happen and then incorporate them, then it will be very, very important. Now, here you can clearly see here system-based modeling and alternative designs exploration. Alternative design means obviously material selection is a part of design. All of us have done in various courses. Material selection is a part of design. Okay, and then the detailed design and prototype time. Now you shall be able to make use of the predictive modeling capabilities available today in various aspects. Okay, and then foresee. Now here you can do total life cycle predictive modeling. Okay, to a large extent, that much facilities are available, still being developed. So by using those tools, it will be very, very important to foresee them. Okay, and then evaluate one against the other designs. Now, and if you see the materials life cycle or closed loop materials flow, now you they will be moving from the materials extraction, you can clearly see here, and then manufacture, distribution, usage, and life end of life management. Okay, but here the most preferred and least preferred, which side you shall landfill as minimum as possible, you shall reuse as maximum as possible. Okay, so you and if not before landfill, you shall try to do the energy recovery, or after that recycle, compost, and whatnot, depending on the requirement. But here you can clearly see reduce at every stage. Reduce at you can clearly see extraction, pre-manufacturing, manufacturing, use stage. Okay, now you shall reduce the material usage in the design. Then today you have a lot of tools, lot of design things, and the corresponding manufacturing processes to implement them. Sometime back, if at all you want to make a component, let's say having the fatigue properties, you might have chosen a forging process. Okay. Forging process has its own constraints, but the today combination of forging and additive manufacturing together give you a lot of freedom, and then you can use the topology optimization and design the component with lesser material and with the required properties. Okay, so there are hybridization of processes also possible in this. I'll show some of them later stage. Okay, now if you are looking at this, basically we are looking into the life cycle and circular manufacturing. Okay, now it's not just during the manufacturing stage alone, but if you take the different components, they will have different contributions to the energy consumption during their material life cycle. If you take aeroplane, the materials manufacturing and transport will not be costing during the use phase, because it will be used for 25 to 30 years, maybe more. I don't know exact number. It will be consuming a lot of, okay, energy. Now, even if your family car, you can clearly see that. If you're a refrigerator, but if you look at a carpet, okay, if you look at carpet, you can clearly see the material cost is very, very high. Use phase is less. Now, depending on the product, the where the energy being consumed, and then, but by taking the total life cycle, one should do what will be the best suited. Okay. Now, how do you use the material information in the design process? Okay. Now, we all know the design process is the process of translating a new idea or a market need into detailed information from which product can be manufactured. You can clearly see there. But if you look at it, market need, problem statement, concept, embodiment, detail. But now, here, when we want to explore the newer materials and all that, at the concept level, you should not say that I'll be using this material, and here you shall explore all the materials. Okay. Now, by the time embodiment comes, you shall be able to say, okay, I'll be using some metal alloys, okay, depending on the properties needed and all that. Okay, and then by the time it comes to detail, you may say that aluminum is most suited for this. Among the aluminum, which one is suited, one shall be able to explore. Okay, but you shall not start with this. In that case, aluminum based on someone might have used, but you will be missing a lot of newer materials and other possibilities present. So you shall have a mechanism to explore all this. Okay. Now, if you go for a material selection, okay, now you can clearly see the what are things which are very, very important. You all have been in design process. Now the properties are very, very important. It may be mechanical, it may be thermophysical, it may be chemical. I just listed some of them. And availability is also very, very important. Economics is, you can't avoid that. And business and environmental issues. Is recyclability an issue? Disposability? We all know various countries, including our own country, we have a lot of issues with some of the disposabilities. Okay. Are the materials hazardous or subject to environmental other regulations? Is there a liability issue? We have to be very, very careful while selecting this. What should be the alternative materials for the same? We shall be able to explore. Now, if you take a typical material selection approach, okay. So now, most of the times, you go with what you are comfortable with, okay, what you are comfortable with. Now, but this approach comfortable with is very very necessary. Let's say if you go for aerospace and other applications, space applications, but I think it's not necessary that you have to use thing. But at the same time, highway bridges and all that, okay, you have to be very very careful, because where the reliability necessary is very very important. They are the codified applications, you have to go with this. But the optimization approach, but this is mainly started with Rush Bay and then people have explored, involves selecting materials based on critical properties with multiple constraints, whatever you have, because I was mentioning about various things one should consider at the start, imposing the selection process. Okay. So generally, very very simple things also one can, simple applications you will be seeing later. There is something called a performance index which will be dictating the major property of that particular component in the product for combining and quantifying the various requirements. Okay. Now, a single property, we have seen the aeroplane wing properties, okay, are rarely the basis of materials. Combination of the various properties, it may be mechanical, it may be physical, it may be thermal, all those combinations are very very important. Sometimes strength and stiffness may satisfy, corrosion resistance may not satisfy. Sometimes strength and stiffness may satisfy, they may not be weldable. Okay, so you have to be very very careful while selecting this. Okay, now let's take very simple example, a transmission line. Okay, high tension transmission line. Okay, let's say if someone poses a question to you, select a material that has lowest transmission losses. Okay, then the transmission loss is basically nothing but heat generated due to electrical resistance. Okay, now you can clearly see I square R losses. We all know Joule heating, and then the resistance should be rho L by A. Okay, now so you have to basically maximize I square R losses. Okay, so you have to see the factor. Okay, how to minimize the thermal losses. Now here, just to understand one factor here. Okay, now that let's say if you take the three materials, copper, silver, and aluminum, will you use silver? No. Okay, you can clearly see the factors here. Not only that, and the properties necessary. If I look at the only resistance point of view, okay, now the electrical resistance is the electrical resistivity is the minimum for that. Okay, but if you see the copper and then aluminum, now the thing is you can clearly see the various factors, but not just this one alone will be dictating. Now let's say when the transmission line is present there, there will be wind loads will be coming. It has to carry its own weight. The cable should not sag. There are other multiple constraints. I'm not listing all of them, multiple constraints which will be coming into picture. They will also dictate. In that times, generally, if at all, the core gets heated too much, then the case, if at all happens, then the heat will be increasing. That will be reducing the strength. Now, can the core be the other material, and case, which generally carries the current, will be the material to be used? And there are many, many things which you can clearly see by typing. There are many innovative solutions for taking care of those. You can see them. Okay. Now, when you are going for an index-based application, which is promoted by Professor Ashby, and it is now available in the form of a software, which is one of the best ones in my personal opinion. Okay, you have selection of engineering material based on the what is the function, target function, what is the objective, what is the constraint, and then satisfying them, you will end up with certain free variables. You cannot play with each and every variable. Okay, function is clear, objective is clear, constraints will be there. Let's say if at all you are building, okay, you have to build within this space. The dimension should not be more than this. Certain constraints will come. Okay, so free variables. Then function, what is primarily expected to perform in surface, support load or sustain pressure or transmit heat, whatever it is. What is objective? Making the component functionally superior but cheap and light and use the minimum material. Basically, when you consider all that, sometimes you may have to minimize something, sometimes you may have to maximize something. Okay. Then what are the constants? Geometrical, functional in nature, corrosion resistance may be less, or some other property will be important. The length of a cross section, length or a cross sectional area of a component in a machine tool may be fixed. Okay. Now, if at all you are designing a lathe, now lathe will be specified by the maximum diameter which you can machine, and then maximum length which you can machine. Then the elements which you choose for the lathe have to be constrained within that. Okay. Now, service conditions to operate at beyond or critical temperatures. Okay. Now, if you are choosing for a aircraft engine to that of automobile engine to that of some other reactors, the entirely different thing, critical temperatures. So when you consider all of this, then you will end up with the free variables. That is where you will be playing with the free variables to select the best suitable material. Okay. Now, now here some details are given. Now you can clearly see material index, which is generally represented by M. Okay, refers to an attribute or a combination of attributes that characterize the performance of a material for a given application, whatever we said above. Okay. The material index allows ranking of all possible materials, engineering materials, in order of performance for a given application. Then you have to select among them, rank the suitable set of materials based on material index. Then it will be much easier for you to pick, to design, pick the material for the chosen the design which you are making. Okay. Now you just take the simple application, selection of material for a light and strong tie rod. Okay. Now tie rod, basically it will be under the tension. Okay. Length L is specified, that is a constraint, must not fail under the load, so the stress level should be below the yield limit. Now the remaining things I don't need, because you all know your bias should be less than sigma y, the mass should be objective to minimize that. Okay. Now area, length and density. Then if you look at all this and then by plugging in this, the material which you have to select is which is having the maximum of this. But now here, sorry, I'm going back, sorry. Now here, one thing is, this is the tie rod. Here, it doesn't matter as long as the cross-sectional area matters, but it can be circular, it can be square, it can be some other section. Okay. But if you look at some sections like a beam, you all have designed. Okay. Now, if you wanted to minimize the stiff beam of length L and minimum mass, then obviously the section thing will come into picture. Okay. Sectional geometry will come into the picture. I'm not going to the simple calculations here. Now, here in this case, the material to be chosen will be self-satisfy this constraint. Okay. Now, when you go for the earlier case to this, geometry factor is also coming into the picture. Okay. Now, what will happen? Let's say if you take this particular square cross section to the beam cross section, a much more complex cross section here, the manufacturing route necessary that must be used to process that shape will be different. Okay. Now, if you take a circular cross section, now many processes can produce that easily. But the thing is, such a cross section cannot be produced by each and every process. Now, you can understand what sort of the constraints and then selection processes will be coming into the picture. So now, these are the type of selection charts available today in the software form, and then they are being added every time a new material comes into the thing. Okay, this covers. Now if at all This is the Young's modulus density. This is the function which you have seen in the earlier application. Okay. Now, you must satisfy your material may have to be above this line, okay, to satisfy that. And then if you want to maximize this, you'll be moving up, okay, and then you will be selecting. Now, obviously, you know the diamond is sitting here at the top. Okay. Now, which one will be satisfying with your constraint cost, this, that, a lot of things have to be considered here. Now, but in this process, you can zero in, you can basically narrow in on the materials which you have to use, and among them you can select depending on the requirements. This is the screenshot from the software. Okay. Now, this will provide you the materials which you can pick. You may think, oh, I'll use alumina, but there may be a composite which will be satisfying the same requirements and maybe a better life, and then you may be able to repurpose later. I don't know. That has to be considered when it comes to the circularity aspects of it. Okay. Now, similarly, you can clearly see how these charts can be represented. You can choose the x-axis, y-axis necessary of different materials and properties, and now they plot the way you wanted, and then you can pick among them which composites will be satisfying the same thing, which metals will be satisfying. Here, the polymers are not satisfying any of that constraints. Then you can pick the materials by further evaluating them. Okay. Now I have mentioned about the shape earlier. Now the tie rod area matters for the beam. The you all know this moment of inertia part of it, polar inertia part of it, and then for the column, I mean matters because the buckling, the unsymmetric loading, how they will be playing the role. You all understand the compo. If you go from tension to the compression, there is a different ball game. You can clearly see all the only the stress reversal occur because the buckling occurs here. Okay. So what is the best combination is very, very important. Okay. Now I will skip this part. It's the same because now if you take the shape factor into consideration, then obviously if at all you are evaluating the four different materials, um, this one basically a steel, a titanium, a GFRP, glass fiber reinforced plastic, and wood. Okay. Now, without the shape factor, that is the phi e, without the shape factor, which material is the best? You can clearly see which one is the best, friends, here? This one. Okay. But the moment you bring the shape factor in and other things, wood may be a better one. So you have to be very, very careful. This is just example is chosen to show the material can be different. Okay. Now, how even the material and manufacturing process is concerned. Now, hot rolled steel, you can clearly see hot rolled steel joist and protruded GFRP channel, extruded aluminum T section, extruded aluminum I section with respect to section area, and then the second moment of inertia. Even such plots can be generated with the data available today in the softwares, because having all the data handy is not that easy without the software form. And then this helps in selecting the materials and the corresponding manufacturing processes which you can procure basically from off the shelf things whenever you are designing, that will be costing very less. But if at all you wanted to come up with an entirely different process, it will be costing more. But if the circularity has to be considered into the picture, how to reuse that, how to refurbish that, how to repurpose that after the first life cycle ends for one particular product, every component life may not be over, then the game has to be different. One has to consider those factors also into the consideration. Okay. Minimizing the impact of production phase. Okay. Now, obviously, you will be spending a lot of energy for the material to extract and then process that material and then convert the raw material into required component geometries at the different manufacturing production phases will be important. Now, the performance indices earlier, whatever I was talking about, only I just showed the process and energy component of it, but without considering the CO2 emissions. But even that has been implemented to a large extent in some of the cases. CO2 emission or eco indicator are derived in the similar way. How much energy is needed and how much CO2 emissions will occur from the extraction stage to the usage stage. And then you can clearly see those factors also can be considered and plots can be generated. This philosophy is the more important thing here. That's why we are not getting into the design or deriving these expressions. They are already available in the literature. Okay. Now, you can clearly see the material selection for considering the ecology or environmental impact. You can clearly see if you take the Young's modulus of the material, embodied energy for a cubic meter, and then you have the various constraint lines. Now, it should be below this or above this, and then you can keep moving the line up or then this parallel to this, and then select the materials necessary. Now, so there are attempts and people are developing. Okay, this is only 3, 4, 5 years back. Okay, you can clearly see that there is a material circularity indicator. Now, the product level material circularity indicator, not the part level. This is, please see this. This is the product level, but you have to go to the part level. That is very, very important as we move ahead. Okay, because the product lifetime may be over first offense, the first cycle, but the thing is, many of the parts may be as good as new ones. Okay, so only 10%, 20% of the components in automobile may not be reusable, but 80% of the components may be reusable by slightly changing the geometry, by repurposing it, and all that. So it may not be 80, it may be 70, okay, or more than 50 for sure. Indicate measures the extent to which a product has minimized the amount of virgin material. You cannot go on exploiting using the virgin material as feedstock. You have to reuse the material if at all you want to care for the earth. Okay, and unrecoverable waste at end of life first, and also how long and intensely it is used compared to similar one. Some expressions have been developed. You can clearly see is the fraction of feedstock from virgin resources. You may be combining some virgin, some already used. W is the unrecoverable waste. And then I'm not getting into this, but there's a very detailed analysis available. You can look into this. And the basically circularity indicators are very, very, and the circularity indicators range from 0 to 1. High MCI score, the better the materials of product to circulate. Okay, so here you can clearly see the material data, product indicators, circularity index. So all this has to be integrated and you shall be able to select and all that. Yeah. So now obviously digitization helps in every aspect of it. Digitization helps in every aspect of it. Now, what we learned is we started with the design and we started with basically material selection. In that material selection, basically when it comes to circularity aspect of it, what are the various important things in the design for circularity? Professor Takata will be covering more in depth. He is the expert in this area. Now, the reconfigurability, you shall be able to reconfigure it. It should be flexible. You shall be using renewable or recycled materials. You shall be able to remanufacture while design. You shall consider remanufacturability. You shall consider the repair of it, disassembly, reassembly, recyclability, and many more factors can be added into this. Okay. Now, you shall basically have to have two bounds: what is the maximum feasible and minimum feasible, and a particular specific products. You shall satisfy the minimum one, try to take every aspect to the maximum extent possible. Okay, like system that enables the design of products under components to use multiple times along with designing out the waste, minimize the waste. That is what designing out the waste is very, very important. Okay. Now, what is the circular design? Resource minimization. It may be material, it may be energy, it may be this thing. Designing for present and future, because you will be using, reusing, repurposing. That is a very, very important thing. Okay. You cannot just take the present case. The future is also very important. Okay. Now, the product level, that's what it is. Reuse, recycle, remanufacture, repair, reduce, redesign, whatever it is. But at the process level, reducing the energy. Okay. Now, as this is topic is related to the material selection and process selection, I'll spend some time on the process selection. You all know all the manufacturing processes which you are using can be covered, can be clubbed or classified into three categories. They may be formative. Okay. I'm not saying metal forming, formative processes. It may be casting, it may be forming, it may be, some ceramics related things, a lot of things basically formative, basically processes, additive processes. You all know the joining and other CVD, PVD, a lot of additive manufacturing processes and removal or subtractive processes can be done. Now, if you look at this particular first, the formative processes, subtractive processes, additive processes, now the colors are not very clear here. The additive process, today's additive manufacturing is this: the cost for component will not be coming down, although you are going to increase not much other than offsetting the original equipment cost. Okay. This will not be coming down much, a small amount may be coming. Okay. But when it comes to the formative processes, when the productivity needed is high or the number of components needed are going up, then obviously cost comes down. Okay. Now, where to use what process, and considering the circularity into the consideration, let's say if at all less number of parts are necessary. Now, you will not be investing in making a forging die, you will not be investing in making a buying a gigantic press, but you may go for additive process, or you may hire someone additive machine for few hours and make the component. Okay. So one has to be very, very careful where, what number of parts and what cost you are interested in putting in. Okay. Now, what are the various process selection parameters which you typically consider? Okay. It's computed by a range of manufacturing processes for the same geometry, same surface properties, and then you may be able to produce by using a number of processes and wide variety of material types commonly in use. Okay. Now, there are around 200,000 materials are 200,000 materials are available today. Yeah, if at all take the alloys, their combinations and all that. Okay, but the digitization is helping to select the better material. Okay, to be competitive, the identification of technologically, economically, and ecologically. These are very three important words: technological, economical, ecological, carbon footprint, and other environmental factors. Feasible process and material combinations. One cannot select the material without considering the process. One cannot select the process without considering the material. They are interlinked. Okay, is crucial. Crucial. So now you can clearly see the quantity aspect of it. I mentioned in the previous slide. Processing times necessary. The obviously the formative processes productivity will be very, very high. Processing times are less, but to start the production process, it may take more time than some other processes. The geometrical constraints, material cost availability, energy, maintenance, environmental aspects, equipment, tool costs, tolerances, you all know it. Okay. Now, you must consider even all these things: process waste, process supervision, while selecting the process. Okay. And material to process compatibility is also emphasized here. Okay. Now, if you see, typically, without going into circularity aspect of it, okay, generally most of the raw materials are available in the powder form and molten material, or you may be extracting the powders, are in ores and then converting into the, let's say, steel. Okay, you extract the ore, then put into blast furnace, put through the process, and then melt it, and then you will be going for a casting and then go through a lot of processes. I don't have to ingot casting or continuous casting, then rolling, then you may be going for extrusion or directly extrusion after casting, forging, like this. Like if you take the polymeric powders, you may be injection molding, you may be firing sintering, you may be pressing and sintering, lot of things. You may be taking a lot of these metallic powders and then solid freeform fabrication or today's additive manufacturing is the another route. Okay. Now there are sequence of steps, but why they do this? Basically, after the casting, the material properties are different. If at all you extrude that, or if at all you forge that, the properties are different. Okay. If you do that at hot, if you do that cold, we all know that. So this is also very, very important aspect of it. Cutting the story short, okay, among what should be the strategy, okay, among considering alternative design solutions for cost, quality, and circularity aspects, it is necessary to explore candidate materials, geometries, why materials important is emphasized already, geometrical aspect is emphasized, tolerances and whatnot, okay, against possible manufacturing routes, selecting appropriate processes. I'm reading this out. This is a very, very important statement. Processes and estimating the costs of manufacturing early on in product development across whole range of options, in addition to understanding the costs of appraisal, inspection and testing, failure, both internal, rework, scrap, design changes, and external, warranty claims, liability claims, and product recall. You can clearly see how intense this statement is. Okay. And now to do this, okay, one will not have knowledge about each and everything. One shall minimize the one shall have the data at hands and then keep developing the data necessary to explore this and then to digitize this. One must have way of exploring conformance levels across the life cycle before a process is selected. That is very, very important. Okay. One must have some sort of a maps or a digitization and containing material suitability, design considerations, quality issues, economics, process fundamentals, process variations, and when it comes to circularity, more importantly, the ones needed for assessing the circularity aspects, one or two of them we discussed earlier. Okay. So one shall have all sort of this data digitized or in some sort of the maps, the way I have shown the material selection in the case of manufacturing processes also. There were some attempts in the name of process information maps, but not much of circularity is considered. Okay, I'll this. Okay, what are the present in this process information maps? Process descriptions, what materials it can process variations, economic considerations, typical applications, design aspects based on what is being used. Basically, this is what is already comfortable with. Okay, design aspects, quality issues about the things basically they try to. But the thing is, this is very generic in nature. If you go to some of the companies, they will have their own proprietary data. They don't share that easily because that's their proprietary one, where the process level, which variable gives, which process variable gives the better quality, which one will be consuming the less energy, which one will be consuming the higher energy, which one will lead to the better tolerances. All the data is available because we all know whenever we have tried, manufactured this thing, we know that thing. Okay. So what will be the typical process? Okay, obtain, estimate the annual production quantity. Okay, material type to satisfy the product design specifications, PDS. Select the process information maps having all the above information. Understand the process and its variations, material compatibility, assess conformance and component concept with design rules, compare tolerances and surface finish requirements with process capability data, consider economic positioning of the process, obtain the component cost estimates. But here, the circularity also must come into the picture. Okay, how easily this can be repurposed, this component can be repurposed, and all that are not present in the manufacturing process selection at this stage. Review the selected manufacturing process against business requirements. This is the typical process which has been proposed without considering circularity. Now, even you can all see that what type of, here also a lot of data is digitization available. Let's say surface finish ranges are achievable. This may not be clearly visible to you of various processes. The what is the best, the dark ones are the easily available ones, the better ones, and then the lower side one basically is difficult to achieve but one hand, but the thing is other side is very easy to achieve. Okay, now if you take a particular process, what sort of geometrical features, shape capability it can produce, you can list a lot of those things. Now, process boundaries, you can explain them. Also, smallest tool size available for a given process, okay, and the largest plane producing processes, whole producing process, largest tool size, and the smallest tool size. What is the negative tolerance you can achieve? What is the positive tolerance you can achieve? By collecting the lot of data, today one can make use of all these newer tools, okay, which are present, okay, data processing tools. Okay. Now, the another approach which people have proposed is the performance constraint mechanism innovation. Now, people have been using such things for some time. Now, let's if you take the lightweight is important. Now, this is related to mostly towards the forming part of it. Okay, constraints, the formability aspect of it, press loads and materials. Now, mechanism, formability is dependent on temperature, stress rate, strain path. Okay. Now, then in that case, if you consider what manufacturing process is more suitable, do you go for a hot stamping, electrically assisted forming, or you go for a laser forming, hydroforming, superplastic forming, or impact forming? Which one is suitable? You shall be able to, okay, or when you go for the incremental forming or vibration assisted forming, okay, and now when you go for a joining, whether you go for a foam forming or joining by forming, okay, you can explore all these processes, and then with the today's predictive tools you can do a lot of computation, and then combining with some sort of machine learning techniques, this can be further improved. Okay, this is for the additive manufacturing aspect of it, particularly hybrid processes. Same thing, property, mechanism, energy source, hybrid AM processes. Hybrid additive manufacturing, you may combine with machining or a cryogenic machining like that. Now you can clearly see, I'll just read out one: hardness, ultimate tensile strength, yield strength, elongation, residual stresses. Now correspondingly microstructure, stress straits, surface evaluation, then the energy source, what you are using in various additive manufacturing processes, and then the various things which will be coming into the hybridization possible, because this hybridization is becoming more and more, because a particular manufacturing process cannot produce a part with the required things, but by combining multiple processes either sequentially or simultaneously, you may be able to get the required thing with a minimum energy requirements, and then to satisfy the ecological circularity aspects of it. Okay. Now, what should be the manufacturing attribute? You shall basically, we all know that today's integrated manufacturing, I prefer to call that way. People may call industry 4.0, 5.0, and then smart manufacturing. Everything is integrated. You have to have customer responsiveness, physical plant and equipment responsiveness, human resource responsiveness, global market responsiveness. The rapid response is a very, very important thing when it comes to manufacturing. This is, and the resource efficiency, environmental footprint that we have been covering. I'll take 1 or 2 more minutes. Then the process selection status. Now, let's say if someone gives you user requirements like this, Today we're talking about cyber physical systems, and all the data is possible to be put into this. Now, can you map them? It's not that easy because with the combinations and all this possible, now people are attempting to develop such things step by step for some group of processes and all that. Okay, but still a lot more work to be done even in the research front. Okay, considering mapping from these and then the considering the circularity levels, etc. Okay, now I just mentioned to all of you the hybridization is becoming very, very important. Now, the way the CARP defined first the hybridization is simultaneous and controlled. There's a simultaneous thing, but that's a slightly narrow definition. Okay, and then different process mechanisms to be used in the same processing zone, basically simultaneous. Okay, but two or more established manufacturing process into combined setup, that is another definition. But the more encompassing integrating definition can be synergetic combination. You have to use the synergy of the processes of two or more different processes to overcome their individual limitations. Each and every process has various limitations. We all know that. Take advantage of their combined strength, produce components more efficiently, eco-friendly than the existing processes. This is where hybridization, this can develop newer processes. That's why there are a lot of attempts across the world in developing the hybrid processes. And then this will be contributing the circularity aspects as well. Okay. Now, I'm only talking about brief about hybrid processes in the case of metal additive. Okay. Now, there are many attempts in the metal additive manufacturing. Okay. In the recent past, particularly last 10 years, right? Deforming the deposited layers. In additive manufacturing, we all know the deposit the layers. So you will be depositing either layer by layer, after 2 layers, 3 layers, or deformation of the deposited component. Deposit the total component and deform it, and then deposition on the deformed component, okay, with respect to metal forming. And you may be doing machining, you may be doing sandblasting, you may be doing other operations. Okay, uh, now you can clearly see the deformation of the layers, metal being deposited, and then basically this enhances a lot of, this solves a lot of strength issues, residual success issues, density issues, porosity issues which occur in the case of metal deposition. Okay, now you can clearly see metal being deposited and then a hammer is pressing it. This also solves a lot of, increases the density, refines the microstructure, and enhances the mechanical properties. Okay, now one can take a sheet metal, and now let's say you can only produce the constant sheet metal thickness. Otherwise, you have to go for a laser welding and all that, But the thing is, there will be a gap between them, and that will become a weaker point. Let's say in the flanging operation, you need a thicker one here. Now, let's say you deposit material on top of that, and deposit the material on top of that, and deposit the component. Okay. Now, you all know the rolling is used for many applications, rings. But the thing is, what they do in the case of conventional approaches, ingot, forged ingot, then punched ingot, and then rolling the ingot, and then finished product. You can reduce the time and then dice necessary, cost necessary if the components required are less. I am placing that if the components required are less. Then powder, deposit, ring roll it, and finish it with the same mechanical properties. It can be, process parameters can be adjusted. Okay, and my friend Professor Surya extensively works on wire arc additive manufacturing at IIT Hyderabad. The components you can clearly see here. But what we do is basically is we combine metal additive manufacturing and bending together. You can clearly see by doing the process parameters and process sequencing and the deposition sequencing and then forming sequence, you can clearly see the components which can be published. These are unmachined components. Even the machining will be incorporated at different stages. and then much more neatly visible components also can be seen. Okay. Now, there are attempts even to combine the forging and metal additive manufacturing to get the things basically. Yeah. Now, we combine double-sided incremental forming and metal additive manufacturing to produce the components in the case of non-planar deposition. Generally, if you take the additive manufacturing, they are the planar deposition. Non-planar deposition is very uncommon. So they're all deposited on the planar substrates. So we do it on the non-planar substrates. First, we form this component using the DSIF. I'll quickly show you the, I hope the video is visible. Okay. Now, there are no, hello?
Yes, it's visible.
Yeah, yeah. Now, you can clearly see no die is necessary to make the sheet metal component. You can do just an NC machine, but it takes more time. Okay. You can clearly see on the machine. If you get time, you can ask Professor Anurup to show it to you. One of the students can help you. Okay. You can clearly see that, and very big component also can be formed just by NC programming it. A lot more mathematics is necessary for generating the tool path. Okay, now all these components are produced by the same tool. Okay, so now you can make the non-planar substrate without making the dies. The moment CAD diagram is CAD diagram is ready, within an hour or 2 or 3, you can produce the component. You can take it to additive manufacturing machine and produce the components. You can clearly see that the complex components without the support structure can be produced. Okay. Now, road to CM. Reduce resources, redesign, rethink the process, repair and refurbish the process, reuse, repurpose for new design, remanufacturing, recycles. Okay, now I'll skip some of these slides, okay, for the time constraint. Okay, now the summary of my talk in one sense is developing a system for circular design. I saw the Professor Taka's title, incorporating all life cycle aspects is necessary. Okay, here we only discussed about the select materials and process selection aspect of it. Judicious combination of different manufacturing processes have potential to enhance product complexity, surface quality, mechanical properties, and structural integrity, and reduce build time, material wastage, and energy consumption. Okay, and ecological imprint. Okay, or basically carbon footprint, with obvious financial and environmental benefits. Okay, thank you very much for your kind attention. Dr. Anurup, over to you.
Thank you. Thank you, Professor Reddy, for the nice talk. If we have some questions, then the audience can ask, and I'll try to relay it back to you.
Yeah, yeah, sure, sure.
Yeah. Okay. The question is, what are the interesting 4.0 technologies for circular manufacturing?
Yeah. See, there is a next lecture. Professor Surya will be covering all the enabling technologies. Okay. Now, as I was mentioning, integration and flexibility are important. All the processes, let's say if you take obviously digitization and then digitally connected tools and digitally controllable tools, I can get into. Okay, someone may say AM, basically most of the books only mentions AM. I have a different view. All flexible manufacturing technologies, okay, which which can respond. There are many processes which are being developed in even in farming today. Okay, farming is one of the complex things because it needs a component specific tooling. People have developed, are processes being developed without tooling, with a lot of use of robots and other components necessary in that. Okay, so in that way, what I say is all flexible and reconfigurable processes with integration across is very, very important for circularity to be responsive to the needs. Yeah, I'll put that way rather than going into each topic. Yeah, I hope that
Okay.
clarifies. Yeah.
Yeah. Yeah. Thank you, Professor Reddy. Any other questions? Okay. Yeah. If not, then once again, I'd like to thank Professor Reddy for giving this lecture at a very early morning. And so, yeah, thank you very much.
Yeah, I sorry I couldn't be there physically because things didn't work out. And see you all sometime. And see you, Dr. Anurup, Professor Takata, Professor Surya. Okay, bye.